I will. I'll try to speak loudly, and if I'm not speaking loud enough, you just let me know. Okay. So, as most of you know, there's a book behind these set of lectures, a book written by myself and my two postdoctoral fellows, Problems in the Theory of Modular Forms. And we aspire to cover one chapter a day. That's pretty tough. So obviously you're not going to be covering every itsy-bitsy detail in such a short course, but the purpose of these lectures is to stimulate your interest to rush to the library right after the class and continue your study in a more detailed form. Is that so I will try to whet your appetite to perhaps inspire you to study these things further. So hopefully these lectures, after the 10 days are over, you will pick up the book perhaps and study it in more detail. You will find that there are more references provided at the end. In fact, the references that have been provided at the end of the chapter also has a short guide to the literature. I indicate which books are accessible to the undergraduate and which books perhaps are a little more difficult. The topic of modular forms is central to mathematics. There's a famous aphorism or joke, perhaps you might want to call it, attributed to Martin Eichler, that said that there are 5 fundamental operations in mathematics: addition, subtraction, multiplication, division, and modular forms. So somehow modular forms are important. That's just meant to be a joke, but the joke is supposed to also conceal a profound truth. First chapter in my book is somewhat unconventional, and I did that deliberately because I want you to understand the origins of the subject of modular forms. The origin seems to be in what's called the theory of Q series. Perhaps beginning with the work of Euler. Is that big enough for everybody to see? Okay. Euler studied the partition function. P of n. So P of n is the number of ways of writing n as A1 as A2 AK. So this is unordered. So it doesn't matter. I'm not going to count 1 plus 2 and 2 plus 1 as different. I'm going to count 1 plus 2 as just one way. So representing 3, I can represent 3 as 1 plus 2, but I can also represent it as 2 plus 1. But I'm going to count 1 plus 2 and 2 plus 1 the same. So if I do that, Euler realized that if you want to study this function, he calculated the first couple of values, but found that in order to perhaps find a closed formula for this, he decided to package it in a power series. So this is a power series. We'll start with 0 and define P of 0 just to be 1, because there's only one way of writing 0 as sum of non-negative things. So there's numbers of ways of writing these things with AI's non-negative. So if you think about it, you can clump together. You can rewrite this as 1 times J1 plus 2 times J2 plus, let's say, K times JK. So in other words, I'm grouping together how many times 1 appears, and I call that J1 times, number of times 2 appears, and so on and so forth. So in other words, I'm actually trying to count the number of ways of writing n in this fashion. And if I think about that, that can be rewritten as a product. So this tallies how often I'm using 1. This is going to tally how often I use 2. This tallies how often I use 3. And when you look at it in the product, the coefficient of Q turns out to be exactly this. So this is how Euler thought of this problem. So I think it's an important, important idea in mathematics. Somehow, when you're trying to study a sequence of numbers, maybe it'll be easier if you can package this sequence in either a power series or some sort of object which you can study and perhaps get a closed formula for. So this is the first observation. Oops, I shouldn't have put the product sign here. This is the first observation that Euler had. Of course, now you can write this as a product because this is just a geometric series. Let's not worry about convergence. So convergence questions will be ignored in this lecture. This is a geometric series. You all know how to sum that. That's 1 over 1 minus q. This is 1 minus 1 over q squared. So this is equal to 1 over 1 minus q, 1 over 1 minus q squared, 1 over 1 minus q cubed, dot, dot, dot. So we have this nice theorem due to Euler that the partition function has a nice generating series inverse. Okay, so this is the first observation that Euler made. And using this, he managed to get all sorts of interesting identities. One of them is a beautiful recursion formula for the partition function, which we'll derive in the course of this discussion. But this is the origin of the topic of Q series. Okay. So you can see now that this product makes its appearance in the context of the partition function. So the way to look at this thing is the left-hand side is a nice series of packaging a sequence of interesting numbers, and the right-hand side is a very neat, crisp-looking function which does not have p of n in it, but I know something now about it, right? So I'm sure that Euler, Jacobi, other people of his time period, what they did was they applied this method of power series to study many, many problems, and they were mystified by the fact that these things have remarkable identities. So these identities were the surprise for many of so they crop up in so many different ways. But the origin of the topic of modular forms is really combinatorial. So that's why I begin this topic of Q series. So the first order of business today will be to prove the what's called the Jacobi triple product identity. It was discovered by Jacobi in 1829. And what this says is that the product And this is valid for x dot 0 and mod q less than 1. So let's not, as I said, worry too much about these convergence questions, but let's just write this down in this fashion. No. So you can see that part of what Jacobi has are terms which appear in the problem of the partition function. So the term on the right-hand side is a product of 1 minus 1 q to the n inverse. So the product of 1 minus q to the n is a thing on this side. So this is already telling us something. This may have some relevance to the study of the partition function. Okay, so this is the triple product identity. Now, when you see it for the first time, you might be surprised by how could somebody come up with something like this. That I will not get into. You can Google it and find out. But what I will do is to show you another paradigm in mathematics which is appearing and is now still in its infancy very much, but seems to be a profound new paradigm which perhaps will shed light on other questions as well. And this paradigm is what's called the philosophy of Q. So Q. So the idea is somehow that there seems to be. So let me say a few words. There seems to be a paradigm a new paradigm in mathematics, and it can be labeled as the Q philosophy, if there's such a word. And the idea is really based on an analogy which at the moment nobody seems to really understand. The analogy is that a natural number, on one hand, seems to can be thought of as the limit of n, q goes to 1, of q to the n minus 1 over q minus 1. Of course, you all know that, right? This because this is just limit q goes to 1 of 1 plus q squared q to the n minus 1. That's just a geometric series which you can sum, and you have this. So when I plug in q equals 1, you end up getting n. Okay? So this basic calculus observation is the starting point of a very powerful paradigm in mathematics, which the physicists are exploiting, the mathematicians, the number theorists are exploiting, and combinatorists are exploiting, the lead theorists are exploiting. So something new and profound is taking place by this observation. The idea is somehow there's a world of q out there, and when I take the limit as q goes to 1, I'm actually back in the realm of natural numbers, so the numbers that we deal with are really some sort of a limit case of a larger world, and so the q world. So that's the idea. So this, you can't call it a theorem of mathematics. You can only call it some sort of paradigm. And this particular paradigm has been used to concoct and construct new functions which seem to be having remarkable consequences in much of mathematics. For example, some of you may have heard of the theory of the finite field of one element. The theory of the finite field of one element is basically the study of FQ, the finite field of Q elements, and somehow try to understand the limit as Q goes to 1. I mean, that idea of what do we mean by the finite field of one element? Well, of course, we don't really mean a one element thing. It can't be that. It's a limit case of some grander thing, the finite fields of Q elements, which you do know about, and that have an important role to play. So in this context, people have been trying to construct Q analogs So there's a kind of a philosophy or methodology, if you want to call it, basically to try to construct Q-analyze of classical functions. And how to construct Q-analogs of these functions is not always clear, but the guiding principle is this observation here. So, for example, we are going to look at first the Q-analog of the exponential function. The exponential function you all know is e to the x, and it's given by an infinite series x to the n over n factorial. So the question then is, what is the Q analog? Now, the philosophy that says replace n by q to the n minus 1 over q minus 1 is not a rigid philosophy. It's a kind of a guiding principle. So when I go to try to construct the Q analog of the exponential function, whatever that may be, I'm not going to change that, okay? But I will change the n factorial. N factorial is, of course, a product of n minus 1 to 1, right? That's your n factorial. So the Q analog of that should be q to the n minus 1 over q minus 1, q to the n minus 1 over q minus 1, over up to q minus 1 over q minus 1. I mean, I'm just going to put that in like that, the way it is. So the analog here that we would perhaps write down is something like that. Let me just up to q minus 1. Okay, so now there's a q minus 1 to the power n here that would appear in the denominator, but that can go to the top, and that'll become x times q minus 1 to the power n, and that's only just changing variables. So probably this is the Q analog of the classical exponential function, and I should think of the classical exponential function as some sort of limit case as q goes to 1 of this higher dimensional incarnation of which this is just a small projection, right? So that's the idea. Somehow the idea is that there's a bigger world out there. Probably we haven't tapped in, we've been fixated on natural numbers that we have not thought about Q numbers. And that's why I put Q series as the opening of this particular chapter. So let's try to study basic properties of the Q exponential function. And out of that we'll pop this out. This will come out. So let's see how that will work. So ignoring any issues about convergence, let's just look at EQ of x. And a small amount of reflection so let's consider this difference, and I'm not actually going to do all this calculation, but it's a small exercise which you can probably do in the tutorial. So you write down the series for this, and you write down the series for this, and you just collect terms and blah blah blah. And what happens? You end up getting x over q, e sub q of x over q. So I'll leave this as a small elementary exercise for anyone to do. I mean, it's not going to be done in the tutorial, but I urge the students to do it. And maybe in the tutorial, if you have questions, you can ask Karamdev and his and me if I'm floating around. Okay, so you get something like this as a functional equation, and what happens is this leads to EQ of x is 1 plus x over q, EQ of x over q. So you can now iterate this one more time. So iterating, you see that this is equal to product n going from 1 to infinity, 1 plus x over q to the n, since a limit as n goes to infinity of e sub q of x over q to the n tends to 1. See, when x is fixed, and q should be thought of here, by the way, in this thing, for convergence sake, this has to be, you have to have q bigger than 1 in this case, okay? So q is the number bigger than 1, and it's shooting off to infinity here, so this is going to 0, so you can see that the constant term is 1 here. Therefore, when the argument tends to infinity, it tends to 0, the limit is 1. So you end up getting this. So you get this nice, neat little product. So the q exponential function that we introduced just by the play of analogy, which is a very powerful method of research, by the way, when you see some phenomenon in one branch of mathematics and somehow mimics something else is going on, there must be a deeper reason for this. And so you try to explore that by building the analogy further. So here, you can call it idle curiosity, but actually there's more profound reason for that. The idea of replacing n with q to the n minus 1 over q minus 1, and then moving to the q exponential function, lo and behold, you end up getting this remarkable theorem. The q exponential function equals this product. So already some interesting things have come out, n equals 1 to infinity, that we have a series, we have an infinite series which is equal to an infinite product. Already something non-trivial has emerged. And of course there's a small issue about q. Q has to be bigger than 1. So you get that. Okay, that's a beautiful theorem in its own right, and we got it essentially for free. Now, if q is bigger than 1, 1 over q is less than 1. So I'd like to actually replace q with 1 over q. Why? Because if I replace q with 1 over q, this will start looking like 1 plus x q to the n. It's starting to look like that product that I encountered in the partition function. Much more natural thing. So we replace q by 1 over q. To get e sub 1 over q of x to be product n going from 1 to infinity, 1 plus x q to the n. So here now, this is valid for mod q less than 1. On the other hand, if I replace q by 1 over q here in the series, what happens? By the way, empty products are to be thought of as 1. Okay, so when n equals 0, it's just 1. X to the n over 1 over q to the n minus 1. So when you simplify all of this stuff, notice that here I've got 1 minus q to the n over q to the n. 1 minus q to the n minus 1 over q to the n minus 1, and so on and so forth. So in the denominator, I've got a q to the n here, q to the n minus 1 here, and so on and so forth. So the power of q is 1 plus 2 up to n, which comes out to n times n plus 1 over 2, right? Okay. So we can simplify that, and see that this is equal to n going from 0 to infinity, q to the n plus 1 over 2, x to the n over 1 minus q. That. Okay, so if you now if you change variables, so we can do that a little bit. So minor changes of variables, basically, what I would like to do is this should have started at 1 and so on and so forth. But anyway, what you could do is this can be rewritten as 1 plus summation n going from 1 to infinity, q to the n choose 2, x to the n over 1 minus q, 1 minus q to the n. So what I'm doing is I just don't want to get stuck at this initial point. Initial point is always 1. Then from 1 onwards, I'm just going to relabel the thing, and you can see that this is essentially n minus 1. It's just changed variables. Okay, so you get something like that. So, in other words, we have the following theorem. There. Now, what's interesting is that on one hand, this is of independent interest. I mean, there's nothing, we don't need to tie it with anything else. It's of independent interest in its own right. But if we come back to the Jacobi triple product identity, we see that it is slowly resembling something of that nature. Remember, on the right-hand side of the triple product identity, we had q to the n squared times x to the n. So in other words, that was like a power series generating function for squares. Somehow, so okay. So now I think we're in a position to prove the triple product identity. So let's do that. So theorem. For mod q less than 1, x not 0, this infinite product is equal to summation n going from minus infinity to infinity, q to the n squared, x to the n. As I said, Euler and company were intrigued by series of this form because of combinatorial questions. So supposing I had knowledge of just this summation q to the n squared, and I was interested in finding out how many ways can I write a natural number as a sum of two squares, then all I would need to do is take the square of this function, and the coefficient of x to the n would be the number of ways of writing n as a sum of two squares. If I was interested in learning how many ways can I write a natural number as a sum of k squares, all I'd have to do is take the kth power of this. Taking the kth power of this is tantamount to taking the kth power of this product, and that should be easy, relatively speaking. So there's some information that's being provided to us by this, okay? So that's the idea behind this thing. So how do we prove this? Proof of this fact, oops, where's the eraser? proof of this fact is, let's see, what place, I think I'll need that. So rub this off. So let's call this equation star. So in star, replace q by q squared and x by qx. Why do you want to do that? Well, it's for the following reason. If I replace q by q squared, the denominator that's in the exponent disappears, right? The exponent here is n times n minus 1 over 2. So if I change q to q squared, the 2 disappears and I get a nice n minus 1. But that's n squared minus n. To get rid of that minus n, I would introduce a q in this fashion to get rid of that thing. So that comes out neat and clean. So we get the following product. Something like that. So I've replaced q by q squared, x by qx. So I end up getting that from star. So that's not a problem. That's clear. So now the trick is to write this denominator here as an infinite product again. So I'll rewrite this. Now don't get confused with, I guess you're finished 4 years of undergraduate study, I hope. So don't get confused with these subscripts that I'm going to now put into the calculation. So it's q to the n squared, x to the n, product j going from 0 to infinity. Divided by product j going from 0 to infinity. So what have I done? Well, this product, I'm starting this numerator from n onwards. So the exponent here starts with n onwards. So what happens is all the terms before n, exactly these terms, will still survive. So you see, these are the even exponents, okay? And what are being canceled by the numerator? Anything from 2n plus 2 onwards is being canceled. Everybody follow this? Okay, so you have an infinite product over so I'm taking this finite product and writing it as a quotient of two infinite products. That's all. So when I do that, what happens is the dependence on n is only in the numerator now, and the dependence on n disappeared in the denominator, so I can move it to the other side, which I will do. So, thus, or maybe I write it, okay, thus, maybe I write it here. So, this gives me there. The point is, I can do this. and I noticed that I've shifted the summation from minus infinity to infinity. The original summation was from 0 to infinity, but I've added minus infinity to infinity because there's actually nothing there. When n is negative, there will be something that will cancel it, so the product is 0. Okay? So it's just a convenient way of bookkeeping. I can shove in n going from 0 to infinity. Okay. Now, all right. Again, we want to use this star. In star, we replace q by q squared. Okay, when we replace q by q squared and x by minus q to the 2n plus 2. So I'm playing on this thing. I'm keeping, wholesale use of this identity. So here I have, again, another infinite product that looks pretty close to that one. So it's not a big deal to see that in order to get my hands on what this thing is, all I need to do is put some specializations for x and in this calculation, which is what I'm going to do. That's exactly what I'm doing. So I'm going to change x here to q to the 2n plus 2 and replace, so thinking of this as a product over j, it'll be q to the 2j, so it'll come out exactly like that. We see that product j going from 0 to infinity turns out to be equal to summation m going from 0 to infinity I will make a long story short by just writing down the answer. So all I've done is basically use this identity with these parameters, and now running out of space. I have a feeling I don't need this thing again, so I'm going to rub this off. Okay, so I think this is pretty clear. You just do the obvious and you collect terms. The indexing is with m. So finally we get that the product in question equals product j goes from 0 to infinity 1 minus q to the 2j plus 2 inverse summation m going from 0 to infinity there's this q squared here. I forgot that. So, okay. So get that, and it is minus 1 to the m, q to the m squared plus m plus 2mn divided by 1 minus q squared, 1 minus q to the 2m. So that's what we ended up getting. And if you think about it, I'm going to rewrite this thing as a product j equals 0 to infinity 1 minus q to 2j plus 2 inverse summation m going from 0 to infinity q over x to the m minus 1 to the m 1 over 1 minus q squared 1 minus q to the 2m times q to the power m plus n squared. That's it, yeah. So see, when I introduce m plus n squared, so the q to the m that's floating around here, I've pulled to the outside. I've got m squared plus 2mn. That looks like m plus n whole squared, except there's a n term missing, so I compensate for that by... by the way, what happened to the x? There was an x missing, right, in this power series thing? I replaced x. X is equal to qx, exactly. Okay, so when I do that, you end up getting this. No, there has to be an x here. See, right? There has to be, so what happened? There's an x to the n, which I forgot to carry over. Right? There's an x to the, so this product here, I'm saying is equal to, this product here is, I'm putting that inside here, and there is an x to the n. So when I calculate that and put that in, it's going to be x to the m plus n, because I just want to get rid of the x to the, I've got an x to the m here. There was an x to the n. So this product is only for this piece inside, but there's an x to the n here.
But even there's q bar n squared also. I mean, there's q bar n squared.
Oh yeah, there's a q power n squared. That's right. That's right. But that's now here. Okay. I think it all tallies. There's nothing. There's no, sleight of hand here. It's just. Oh, the n on the right hand side is the n here. On the left hand side. Oh, yes. Oh, yeah. You're right. I forgot to put, you're right. There's a sum here over n. Thank you. Yeah, thank you. There's a sum over n. Yeah, that n is different. Sorry, I shouldn't have confused you with that. There's a sum over n. You're right. Sorry about that. You're right. That n has not, I mean, this is the index here, so that should, so the n that's here should have been, there's an extra summation. Sorry about that. Okay, well, it's, this is all just basically, you need sufficiently long paper in order to calculate all this stuff, which is what, people like Ramanujan, Euler, and they were not timid to do this type of stuff, and you shouldn't be either. So here we are, we've got this calculation now. Now the question is, of course, you'd like to group together these exponents. And the point is that m plus n as for a fixed, so we interchange summation. So let me just say this. Look, this is not what they say, it's not Brahmavidya, so you just need to do the right manipulation, interchange sums. And you change the m plus n squared to n squared. The idea is that if I interchange sum, I've got the m outside and I've got the n inside. For a fixed m, as n runs through all the integers from minus infinity to infinity, so does m plus. Okay? So therefore I can make this change to n squared. And finally, you end up getting that this is equal to product j going from 0 to infinity, 1 plus q to the 2j plus 1 over x. I'm using the theorem one more time, right? I'm using the product formula. So here, let's just go this carefully. So I'm saying that this is equal to summation, a product j going from 0 to infinity, 1 minus q to the 2j plus 2 times summation m going from 0 to infinity of q over x to the m minus 1 to the m times the summation divided by this product, 1 minus q squared, 1 minus q to the 2m. And inside here I have summation n going from minus infinity to infinity, q to the n squared, x to the m, which is the stuff that I'm after, which is the stuff that I have. But what are these factors? Well, one of the factors is this guy, which I can, there's an inverse. There was an inverse here, okay, which I can move now to this side. And then I have to recognize what is this guy, this series. I go back to that Q exponential thing again and recognize that it's that infinite product with the 1 over x. Okay, it's Q over x. So when you use that, so we're using that star identity several times in the course of the calculation. Okay, so I hope that more or less gives you a flavor of how this triple product is proved. It's pretty, it all comes from the Q exponential. All right, now, one of the beautiful applications of this particular identity is to the study of representations of natural numbers as sums of squares. So this identity here is useful because the so-called theta function already appeared in mathematics at the time that people like Jacobi were studying it. It already appeared in the context of the heat equation and so on and so forth. So if we specialize the classical theta function, which also was studied by Riemann in deriving his functional equation for the Riemann zeta function, is where z is in the upper half plane, which we will meet later on in this course, consisting of complex numbers with positive imaginary parts. So that's what's called the upper half plane. If I'm sitting in the upper half plane, the q, the absolute value of q is less than 1 and everything converges. So this is a nice function which is holomorphic in the upper half plane. And so the properties of this function are central to Riemann's derivation of the analytic continuation and functional equation for the zeta function, which of course is not a topic in this course, but it's an important function. So when people see, hey, that stuff has appeared here and it's being represented as a product, there's something profound going on. That should be clear. So if we specialize, if x equals 1, and we specialize, we see that product summation minus infinity to infinity q to the n squared can be written as a product, as an infinite product. Which is an identity of independent interest and beautiful in its own right. So that's an amazing calculation. Now we did it with bare hands, nothing. That's the first point. I think Euler noticed that you could write down other interesting things. Jacobi also noticed more things, and so let me kind of quickly tell you about those things in the time remaining. So here are a bunch of exercises that we could kind of do after we have. Okay, so let me just give you some of the corollaries of this thing, and you can try to do them. It's just a matter of plugging in, specializing values of x and q, and so on and so forth, right? So here are corollaries exercises. Corollaries. What's called the Euler pentagonal theorem. Pentagonal number theorem. Okay, so from here, we want to get to that kind of relation. So it's just a matter of giving 2 minutes of thought to how you would do that. And you can immediately see that you want to replace these guys by something like 1 minus q to the n. And so there's a little trick. So hint, replace, so you can probably do this at lunchtime, replace q by q to the 3/2 and x by minus q to the minus 1/2 in the Jacobi triple product identity, and twiddle a little bit, and lo and behold, you get this. Okay, so you just have to do that. This is corollary 1. Corollary 2. Oh, before I move to corollary 2, let me just point out, you will remember at the very beginning of the lecture I highlighted the partition function problem. So summation p of n q to the n going from 0 to infinity was the product n going from 1 to infinity 1 minus q to the n inverse, right? We got this at the very beginning. Well, now we have a formula for this. So what Euler sees is immediately that if this is the inverse of that, we see that immediately k going from minus infinity to infinity, minus 1 to the k, q to the k, 3k minus 1 over 2 times this partition function equals 1, which means that the only coefficient is the 1 coefficient, everybody else is 0, so this allows you to get a recursion relation for the partition function. And this is how Euler studied the partition function and calculated all these values of the partition function to huge numbers. And you may wonder, how in the world did he do it? Did he actually write down all the ways of writing 10 million as a bunch of summands? No, he used this recursion. So this is an important step, and this is the interest of Euler, purely combinatorial gadget. And by the way, why these are called pentagonal numbers is if you try to stack oranges in some sort of pentagon, just try, put oranges in a pentagonal shape, the sequence of numbers is like this. These are the only things that you get. So that's why it's called pentagonal number. Second corollary is Jacobi's formula, which is also going to be useful later on. So this is Jacobi. And how do you get this? Replace x with minus x. And factor 1 minus xq out and take limits and take limit as q goes to take limit as x goes to 1 over q. So this is a little tricky, and maybe this can be covered in the tutorial in the afternoon. You just need to do L'Hopital's rule and whatnot. Okay, so we'll leave it at that. Okay, so these are two very classical theorems this falls under the combinatorics chapter, and this actually falls into the number theory chapter. It'll be useful later on for other purposes. So the Jacobi corollary is slightly a little bit more difficult than the Euler corollary. Oops. And so let me just give one more exercise which will be useful in a moment. And these exercises you can do in the afternoon tutorial. Yeah, so I'll leave that for you to do. Okay, so now let me, in the half an hour remaining, let me give you a taste of two applications. The first I will do in detail now, and second will be done by Karamdev in the afternoon. And this is the classical question of how many ways can I write a number as a sum of two squares? And the corresponding question, how many ways can I write it as a sum of four squares? So the four squares will be handled by Karamdev in the afternoon using exactly similar method, but I will now show you in detail how to answer this question. This question can be approached in other ways. I mean, this is not the way to, classically, the way of representing a number as sum of two squares, the classical approach is through Gaussian integers, ring of Gaussian integers. And the ring of Gaussian integers, for example, consists of all integers of the form a plus bi with a and b integers. And the norm of a Gaussian integer is a squared plus b squared. So you recognize, you change the problem of how many ways can I write a number as a sum of two squares as asking how many Gaussian integers are there with a norm n. Okay? And then that takes you into the algebraic number theory route. And you can answer the question using the arithmetic of the ring of Gaussian integers, which probably some of you have already seen in some basic course in algebra. Here, we will take a combinatorial route. We'll take the route that we just figured out. So, Jacobi two-square theorem. Let R2 of n be the number of ways, number AB, with a and b integers. Then R2 of n is equal to 4 times d1 of n minus d3 of n, where d1 of n, di of n is the number of divisors of n, with d congruent to I mod 4. So not only is Jacobi going to answer the question, he's going to give you a formula for the ways of a number of such representations. And the same thing will happen with four squares. You're going to get out of this method, you're going to get closed formulas. All right, so how do you do this? We do this by using the triple product identity. You see, people keep writing Jacobi triple product identity and not shorten it to Jacobi identity because there's a Jacobi identity in the theory of Lie algebra, so you don't want to get that confused. So Jacobi triple product identity. The way we wrote it. So that's your identity. So we'll keep using this. The product here goes from 0 to infinity. Okay. So now, how do we solve this two-square theorem? Well, so the proof of this theorem, proof of the Jacobi two-square theorem, begins by, this is due to Michael Hirschhorn. So in the triple product identity, in Dagger, put a to the 4 q for x, q squared for q, to get I'll tell you in a second what the motivation is for this. But let's just understand the steps to start with. So if I change, in this x, I'm putting a to the 4 q, right? So I'm going to get, and I'm changing q to q squared. So by changing q to q squared, I'm going to get 4n plus 2, and the extra q that's coming from x will make it 4n plus 3. And here it'll be the other way around. So I'm getting numbers congruent to 3 mod 4, numbers congruent to 1 mod 4 this way by this process. And then this term here, of course, is when I change q to q squared, they'll all be multiples of 4 by changing the index of summation. You get that. Okay. So that's basically how you get this. So this is not a big deal. So now multiply both sides by a, and differentiate with respect to a. So a is being thought of as a parameter. So if I multiply this by a and differentiate with respect to a, well, what do I get? I have a to the 4n plus 1, and I'm differentiating a to the 4n plus 1. That's going to be 4n plus 1 times a to the 4n, right? So that I end up getting summation 4n plus 1, a to the 4n, q to the 2n squared plus n. And on the right-hand side, I'm supposed to multiply by a and take the derivative. Okay? Well, a times some function, I have to differentiate. Well, use the product rule. So it's easy to differentiate a. That's just 1. So I end up getting this product. Put it like that. And then I have to keep the a and differentiate the product. Right? I mean, that's the product rule. Now, when you want to differentiate some product, it's useful to do the following, make the following observation. If P of A is product n going from 1 to infinity, some Fn of A, then by taking logarithms and differentiating, logarithmic derivative it's called, you end up getting P prime of A over P of A is equal to summation fn prime of A over fn of A. So that the derivative that I want to now look at can be written as a product of P of A times the sum. Okay, the P of A now would be nice, this factor is there, so I can kind of move it out. So it should be clear then, we get this way, we obtain summation from minus infinity to infinity, 4n plus 1, a to the 4n, q to the 2n squared plus n equals this product times 1 plus, well, there was that a there in front of that thing, and then differentiating it. The differentiating turns out to be a nice sum. It's n going from 1 to infinity, 4a cubed, q to the 4n minus 1, divided by 1 plus a to the 4, q to the 4n minus 1, minus 4a to the minus 5, q to the 4n minus 3, divided by 1 plus a to the minus 4, q to the 4n minus 3. So, oh, there's a minus, yeah. This is a minus, yeah, here. Oh, is it 1 minus? Oh, maybe I copied it incorrectly. Yes, you could be right. What do I have here? I actually copied this thing wrong. So when I multiply, when I change variables, you know, make this should have been a plus sign here. It should have been a plus sign here. First term where? Oh, did I make a typo there? Oh, you mean the first? Yeah, the first term. That's right. Yeah, this one. Yeah. Sorry about that. Okay, so when you work it out, you end up getting this. There's nothing. As I said, this is not Brahmavidya to manipulate these power series. So it should be pretty straightforward. And the final punchline here is that we put a equals 1. To get I think there's a typo in the book. I think the sign, you know, this should be, so what's happened, this has got to be minus sign. There's a small typo on page 8. This should be, I think it should be a minus sign. Because what will happen now is I expand, so let's try and understand this. I expand two things. One important point, I think I rubbed off one of the earlier exercises. In the earlier exercise, I gave you that the left-hand side can be you can use the triple product identity again. So the Jacobi identity, rather, the corollary. Remember the corollary that we had? So using Jacobi's corollary, the corollary 2 that I wrote down, Jacobi's, the cube of 1 minus q to the n cubed was the thing, right? That one, using that, and exercise 1.2.4. Everybody has a copy of the book, right? It's part of the package, right? Everybody's got a copy of the book. Okay, so exercise 1.2.4, which I wrote down earlier, if you use that, you end up showing that the left-hand side shows that the left-hand side equals product n going from 1 to infinity, 1 minus q to the n cubed. And so, and when you use the, which can be rewritten I'm just separating out the odd numbers and the even numbers, and this is 1 minus q to the n cubed, so I can partition those into odds and evens and rewrite it like this. And then you do some rewrite this a little bit in such a fashion that you end up getting that this can be rephrased, reformulated as being n equals 1 to infinity of 1 minus q to the 2n minus 1 to the power 4 and 1 minus q to the 2n squared. And this, if I had 2 here and 1 here, 2 here and 1 here, notice there's this triple product again. It's summation q to the n, it's this. Essentially, it's this. Okay? So this is a square, therefore, the left-hand side is nothing but summation q to the n squared squared. The left-hand side is exactly what you are interested in, the number of ways of writing a number as a sum of two squares. So that's actually calculating the number of ways of writing the sum of two squares. And so the right-hand side, though, is non-trivial. So so after having pulled it all out, you end up getting that this is equal to, there is still a sign error, isn't it? Maybe there should have been a plus. Anyway, let's just look at these terms here. Q to the 4n minus 1 over 1 minus q to the 4n minus 1 can be written as a power series So there are multiples of 4n minus 1. And the other ones are, maybe the sign was right. Maybe that was the right one. Because 4n minus 1 is a 3 mod 4 business, right? And then this one is going to be 4n minus 3. 4n minus 3 is essentially 4k plus 1, okay? So minus 3 is plus 1. So you get that this is actually this could be rewritten as a power series with powers of q, but you're factoring the number, the coefficient of q to the m will be the number of ways of writing m as a product of something congruent to 1 mod 4 or 3 mod 4, depending on the sign. So when you piece this all together, along with this other part of the thing, you get that explicit formula that Jacobi had. So as I'm going to be running out of time pretty soon, I just wanted to make some concluding remarks, but I hope it's clear that this remarkable application comes practically for free. The idea of introducing this parameter a and then differentiating with respect to that a is a standard trick that goes back at least to the 16th, 17th century, because when you meet integrals, if you want to evaluate them, a standard trick was to introduce one more variable and then see if it satisfies a differential equation, solve the differential equation, and therefore solve the integral. I mean, that kind of trick was pretty much in the subconscious mind of many people like Jacobi and others. So it's not a surprise to do that kind of trick here as well. So that's about the only new idea that's needed in order to get the two-squared theorem. And a similar, maybe more detailed, careful derivation in the afternoon will give you some 4 squares. So for those things, you get these beautiful applications. Finally, before we stop for the day, in the book, Jacobi 4-square theorem is proved by using a technique of Ramanujan, which is, in a sense, more complicated than this. But Karamdev's presentation this afternoon will show you that the same idea can lead to similar results. So in the few minutes remaining, I just want to say that the theory of modular forms in many ways starts with the 1916 paper of Ramanujan. Although modular forms were being studied much earlier, somehow Ramanujan in his 1916 paper was intrigued by this product, which is now familiar to us. You see, we met 1 minus q to the n cubed was Jacobi's identity. Okay? 1 minus q to the n was the Euler identity. So the thing to the power 1 was the Euler pentagonal theorem. To the power 3 was Jacobi's thing. So you may ask, are there other powers for which you can get some nice results? That's a very loaded question. And the answer, surprisingly, is in Lie theory. Has something to do with affine root systems. But Ramanujan noticed that just as we were able to get nice formulas for the number of ways of writing n as sum of 2 squares and now 4 squares in the afternoon, is it possible to do other powers of k squares? And it turns out that you can, and you can get beautiful formulas all the way up to 22. And the problem arises when it's 24 squares. And when 24 squares, this is the function that kind of enters the picture to mess up the calculation. You don't get an exact formula like the kind that we just wrote down. You get an exact, part of it is an exact formula, but part of it is a problem term. And when you expand this in an infinite series, as a Q expansion, you get some coefficients, and the Ramanujan called these the tau of n. So this is called the Ramanujan tau function. And in his 1916 paper made fundamental conjectures about the tau function. Firstly, that it was multiplicative. Tau mn is tau of m times tau of n whenever m and n are relatively prime. Then he made some conjectures about various estimates and so on and so forth. And that was the paper that somehow spawned the development of the theory of modular forms. And it was only in the 1930s that Hecke came up with the proper theory in order to understand what's going on here. So that's taken up in the subsequent lectures and subsequent chapters, but that's basically where we're going. And I hope I have stimulated your interest in trying to study products of this shape, which will appear throughout this course. Okay, voila.